steer arrive behavior and we have the steer separation behavior. The next thing what we want to do is we want to combine the two behaviors. We have, let's remember, we have a target point, an arrival point, and if we use our arrive behavior, the agents are arriving to this point. Let's talk in the real-time mode. It's not so fast. It's arriving to this point, and if we are using the separation behavior, they are trying to avoid other agents. Let's make the neighborhood radius smaller. Okay. And next thing is we want to use both of them. The problem is, let's take a look in our code. We are setting the acceleration attribute here, and this is a problem because if we are setting the acceleration attribute here, and on this position the separation behavior is overwriting this attribute. So what we could do is just adding the new force to the acceleration attribute. What we are doing here, we are calculating a force, and the next node is adding its force to the prior force. And this is working, and let us see what's happening if we press play. We can see that the agents arrive at this point and stopping at this point, and at the same time they are avoiding each other. But let us take a look to different mind algorithms and remember our requirements. We want a modular system. This is a modular system because we are using different nodes for different behaviors, and we can combine them like we want, and we have nodes for each behavior, and we want to support different mind implementations. And if we sum up just the forces, this is a specific mind algorithm. This is a simple mind algorithm, and what we have to do is implement a mind within the solver which is deciding how to weight this specific behaviors. Let's take a look to two common mind algorithms, the simple mind and the priority mind. And what is simple mind? Simple mind just sums up all behaviors like we did in our test. Here these numbers are priorities. Each behavior has a priority, and simple mind is just multiplying this priority with the steering force and sums up this values, and this results to the final steering force. This just means that behaviors with lesser priority doesn't fall as much into the weight as behaviors with higher priority. The priority mind sorts all behaviors by its priority. In our case, the importance behavior is our obstacle avoidance with 0.6, and stacks up this behaviors, and it cuts up the behaviors which exceeds over the max priority of 1. This means we have 0.6 plus 0.3, and remaining is 0.1. This means just a value of 0.1 of the arrived behavior falls into the calculation. If obstacle avoidance returns in zero force, for example, if there's no obstacle, we have this two behaviors with 0.3 and 0.2, and they will fall fully into the calculation because our max priority is 0.5. The advantage is in priority mind is that behaviors with higher priority can eliminate behaviors with smaller priority. Let our steer solver do this final steering calculation. So we can add our mind algorithms within this solver, for example. And what we have to do is our behaviors just adds an attribute with the behavior force, and the solver is collecting all the forces and is calculating the final steering. How can we do this? Let's edit the arrive code. The first thing we need is a priority float. Priority. And initialize this with 1.0. And on this position we are setting the acceleration attribute. Now we remove this and we are adding an attribute which is read by the solver. Okay, let us create a variable called steer. This is the local steering, and add this steer. Okay, add an attribute with the add attribute vex function, call our attribute steer force, and add our value we use our steer. Let's test compile. Everything is working. Oh, let's add on the attribute too. Attribute steer priority apply. Okay, let's open the spreadsheet on this point, and what we can see here here is our steer force and the steer priority. The problem is if we do the same on the steer separation, we are overwriting the steer force, and we need a counter to count all the behaviors and add an postfix to our attribute so that we can collect all forces. Let's edit our vex function again and insert and steer and behavior counter. We use an integer for this, call it steer count, set it to 0 and read this steer counter, because if there's a behavior connected before this node, we need the steer counter at this position. Steer count. Here with the import, we are importing the steer count attribute and write it into the steer count. We use the first input of our behavior node. Now we want to concatenating this steer counter to our attribute name. This means that we have steer force 0, steer force 1, steer force 2. How can we do this? The vex function provides a function named concat, which is concatenating two strings, and as second parameter for the concat we need a string 2, and but we have an integer here. We can convert this integer to a string via the sprintf function and specifying an integer attribute. It means with d means integer, and as second parameter of the sprintf we use the integer. We have the steer count, and now we are concatenating steer force with the string representation of the steer counter. And the same thing we will do for the steer priority. Let's add concat sprintf steer count, and that's all. Let's test compile. Compile was successful, and take a look to our spreadsheet, and you see we have the 0. And we just forgot one thing. We have our steer counter. We have to increment our steer counter on this position and set the steer counter again, so that the next behavior can read this counter and attach it to its steering force attribute. Test compile, and now we will do this for the separation behavior. Just copy this code and open the separation x function and insert this code into okay. And now we have the separation is our separation calculation. This is not correct. We have to move this up here and let's call this steer, and this is our steering force for the separation. And now we are doing the same as we did in the arrive behavior. We are reading the count, which is in this case is 1, and we are adding the 1 to the steer force attribute. And now if we take a look into our spreadsheet, we can see that we have steer force, okay, we have to select this, steer force 0. Let's go to the next position, steer force 0, and we have steer force 1. But since this is a simulation, we are adding each frame. We are adding we are increasing our steer counter, and we are adding a new attribute, and so we have to reset our steer counter in the solver. Let's demonstrate this. We have the spreadsheet, and if I go to the next frame, we have steer force 2, next frame we have steer force 3, and every frame we have a new attribute. This is wrong. So we have to reset our steer counter in the solver, so that in the next time step we have in the beginning we have a steer counter set to 0, so we can count up each behavior. So we have steer counter 0, 1, 2, and so on. So we can concatenating all behaviors the same way and decide in the solver and we can access all attributes in the solver and decide the final steering in the solver and implement different mind algorithms in the solver. Let's edit the vex function and steer solver. Let's create an integer steer count. Oh no, this is not necessary. We can just add attribute steer count value 0. This is resetting our steer counter. Just take a look into the separation. I think I forgot something. And just compile. And we see we have an error here, a compiling error. This is because we forgot the priority. Let's add the priority float priority, and let's test compile again. Okay, here the next thing is we have syntax error in line 24. This means here. Over here we are defining a new steering, a new vector variable, and so we have to assign this and not adding it to the variable. Let's test compile again, and now the compile is successful. And now we can take a look to the spreadsheet, and you can see we have steering force 0 and we have the steering force 1. 0 is the first one, is the arrive behavior, and the steering force 1 is the separation behavior. And now we can implement a simple mind algorithm in our solver. But if we take a look into our code, we have on both behaviors, we have the same part of code. This is, we could source this out into a header file and define a function which can be called here, but just for avoiding redundant code. But let's leave this for now. For our purposes, this is okay. Just for demonstrating the system. Okay, let us integrate this into the steer solver, the mind implementation to the steer solver. Let's edit the vect function, and what we have to do is we have to calculate a final steering. Let's create a vector and call it final steering and initialize it to 0. Now let us iterate over all steering suggestions from the behaviors. What we need is the steer count, and let's import our steer count attribute and create an integer. And now let's iterate over all behaviors. Let's start by 0, and condition is our counter is smaller than is the steer counter, and increment I by 1 each time. This statement a loop which is called steer count times, and each time the I variable is increasing by 1. And within this loop we can access all behaviors and by using the index with I. Okay, now let us import our behavior force. This can be done via the import, and our behavior is called steer force, and now we have the same problem as before. We have to concatenating or adding the number of our counter here, and this can be done via in the same way via the sprintf, and using the counter, and here we using the %d again. Now the sprintf is replacing the %d with this value set in the second parameter here. The next thing is importing our steer priority. Store it into steer priority. Now then we have to define the steer force and the steer priority. We have the vector steer force, and let's initialize it to 0, because if this attribute does not exist, we need an initial value for the steering force, and as well we need a steering priority and set it to 1 initially. Now we are iterating over all our steering forces, and now we just implement our simple mind algorithm, which is just multiplying the force of the behavior with the priority and sum these values up. Our final steering is the steer force multiplied with the steer priority. After this loop we have a final steering force with which we can solve our point positions and update our point positions. Now let's remove the acceleration attribute and add our final steering variable. Now everything should work fine. If we press test compile, we have an error in line 14. It's a typo problem. We have sprint f as print f. Let's test compile again. Okay, successful, and press accept. Now let's test our implementation. Press play, and you see the arrived behavior is not working. Let's take a look in vex function. Compile is successful. Here we are adding the steering. Oh, this this we changed the acceleration attribute to the steer variable, so we have to change this here too. We have to use the steer variable, not the acceleration variable here. Steer. Accept. Now let's test it again. And now we see that this is working. And now we can play with the parameters. If we disable the arrival behavior, we just have the separation behavior, and if we have just the arrival behavior, the separation is disabled. And let's decrease the priority of the arrival, for example. This means we see the different behavior here because the weight of the separation is higher, and that's why the separation is carry more into the weight. We can also change the radius to make the distance smaller. Here what we see here is that the points may come very close, and because our radius is very small, and if they come very close, the force may come very big, the separation force. This we can take a look in the vex function, and here we are dividing by the distance of the agents, and if the distance is very small, this equation becomes very big value. And what we have to do is we have to do the same as we did for the arrive behavior. We have to limit our steering force to a maximum, to the maximum length of 1. Let's maximize our steering force by normalizing the force and clamping the length between 0 and 1. Accept. And now let's test again. So we can see that the force is limited to a maximum force, and that's why they are not exploding. Finally, let us make the parameters here more meaningful, and because this is the parameter names are the names of our variables, our input variables of our vex function, and we cannot change this via the parameter interface. They are locked because they are directly defined by the vex function, but we can change this. We just have to add pragma messages, pragma statements here in the code, and with the pragmas we can define how the UI should look like for the parameters. And we want, for example, want an op path not to, we had to add the op path manually, but we want to have the ability to select a node, and this can be easily done by adding pragmas are starting with an hash, sorry, pragma, and then we can pragma hint. Then we use the op path. Hint is a statement which is saying that the op path is needs a specified UI type, and in our case it uses a op path type. You can take a look into the Houdini documentation to see all the pragma messages. Just go into the Houdini documentation, into the Vex documentation, Vex compiler pragmas, and here you can find documentation of all the pragmas available in Vex. And we are using for now the hint, and we can specify different hints. For example, if this is a toggle, or if this is should be a color selector, and in our case we use an op path. And here the parameter is an object path, and you can optionally specify an op filter if you want to use just, for example, geometry paths or shop paths or something like this. Okay, we have here the op path. Press apply, and we can see that our op path is now changing, and we have icons to select an op path. If I press here, the operator chooser is open, and this is more handy. And now the next thing, let's change the name of our parameters. We have pragma label, and then we have to specify our variable name, in our case, for example, op path, and then we can specify the label of our op path. Let's call it target object. Then let's define a label for the max radius. Call it max radius. The same for the force scale. And for the priority. Press apply, and we can see now we have a more nicer labeling for our parameters. This is the same we can do for our separation. For our separation, we always need as point cloud path, we always have to use the op input, and we want to hide this parameter and set this to as default value. And we can do this in the Vex editor. Just add pragma hint PC cloud. Oh, I have two C's here, I see. I mean point cloud path. With the invisible, we can remove our point cloud path parameter. But we have to set our default here to the op input path, because we are not able to enter it anymore. And let's enter this here, op input path. Oh, I have German keyboard, so I can't type the inverted comma. I have to copy paste it from my other location. Okay. Now we have set our default point cloud path, and the problem is there are special characters here. For example, we have to escape this special characters. We have to escape the double quotes here, because we have two double quotes surrounding here, and that's why we have to escape this, that the compiler knows that this is a string representation here. Let's do test compile, accept, and now we have our point cloud parameter removed. Only we can add also some nicer labels here. Radius for scale, and the same for priority. Okay, now we have a nice labeling here. And now we have our simple mind and our first behaviors, and let's switch to the next chapter. In this chapter we will